Good evening all of you. My name is Anil Yadav and this is the tutorial 11 on fundamentals of micro and nano fabrication. So I am following the lectures of Professor Sushovan Awasthi from IISc Bangalore, so you can also refer to his notes for further information and for further queries. So today we will see some additive processes that we have already seen some of the additive processes. So today we will go through the chemical vapor deposition, and we will revise some parts of the additive processes like chemical vapor deposition and atomic layer deposition. Okay. So there are various types of two types of deposition we can say mainly. One is chemical vapor deposition and another is the physical vapor deposition. In chemical vapor deposition we take the we take the substrate, and over that substrate or something, when we want to do whatever material we would like to deposit, that reacts with at the surface of the substrate and gets deposited over that. And in physical vapor deposition we already have that material, we evaporate that material and we physically that material gets transported from where we evaporate to the substrate. That's the thing. And the whole material, like if you would like to deposit some silicon dioxide, let us say, you will have a source of silicon dioxide, and then you can with the help of e-beam electron beam deposition, you can electron beam evaporation deposition, you can use that SiO2 to deposit over your substrate. Okay. And on the other hand, chemical vapor deposition is like we use precursor gases, they are they react at the substrate and then the material gets deposited. Like for silicon dioxide we can use silane gas and oxygen. Okay, so this silane gas will be converted into silicon, and that will react with it will form SiOH, and that SiOH will then convert it into silicon dioxide. That we will see on the subsequent slides. And there are some pros and cons of the chemical vapor deposition that we will see. Like the deposited materials is chemically synthesized at the substrate. Okay, not like physically transported. Okay, so there are various kind of CVDs are there, chemical vapor deposition kind of are there. So metal organic CVD. Okay, my laptop is okay, not good. So, and another one is the vapor phase epitaxy. And then comes the atomic layer deposition. We will see the chemical vapor deposition and the atomic layer deposition. How does this processes are evolved? Okay, so better in this through this method you will get a very good quality of material. After that, this is kind of a epitaxial layer growth. So it with that for if you are going for a very good electronic grade of silicon dioxide you need, then it is very good. Okay, electronic grade dielectrics. So this is very good, and and it is a bit costly. Not a bit. It is very high costly, and a bit complex. Okay, that we will see the design of the CVD reactor, and in the last slide. So used for semiconductors, dielectrics, coatings, sometimes metals. So mostly like silicon, you can from silane you can deposit, germanium you can deposit, gallium arsenide you can deposit through there are various precursors for these kind of materials that we will look what are the precursor. Like for silicon if you would like to deposit silicon, silane will be there, silicon dioxide also for silane will be there, and you can deposit tungsten, platinum. So and tungsten is very hard to deposit through the vapor phase vapor phase deposition technique, or this physical vapor deposition technique. So because the tungsten has very high boiling point. Okay, so to deposit tungsten you have to go very low vacuum and very high temperature, and also you need to find a material that can withstand till that temperature, that should not get evaporated, in which we can fill the tungsten. Okay, and moreover, when you see the vapor phase deposition, there is a bot. There are various kind of bots. The bot itself is made up of the tungsten because of that high boiling point or of this one. Okay, so tungsten is very hard to deposit with the physical vapor deposition, so that's why. And there are some terminologies, some kind of metrics you need to take care of. So what is the uniformity of the material or the substrate? Okay, so let us say this is our substrate, and over that you would like to deposit silicon dioxide. Let us say you would like to deposit silicon dioxide. So if the silicon dioxide is like this, so the thickness of the material at this point is lesser than the thickness of material at this position. Okay, so this is highly not desired condition. Okay. Now this is how highly undesired thing, because if you for the further processing, if you would like to etch this silicon dioxide, so this can be the condition when you have optimized your recipe for this kind of width. Okay, this height, for this height you have optimized your recipe. This height is lesser than the height that you have, and this height is larger than that one. So in this one, this layer is not removed, and we wanted to remove this one. Okay, and this is perfect at this position, and it is our rest. Whatever feature size you wanted to get is W, but you are getting a feature size of W plus delta, which was not desired. That's why this uniformity is a critical parameter for the further processing of the of for your electronic applications. And so, and if you would like, if you okay, I think someone would like to let me check once. So now, okay. Non. So for most of the processes other than CVD, ALD is kind of conformal growth and highly uniform kind of of technique that we will see why. Okay, and also CVD is a very good uniformity because of the gaseous precursors we are using. We are not depositing physically. So, and also while doing the physical vapor deposition, so in the physical vapor deposition, what happens, you have a material over here, you want to deposit over that. Okay, so in that case you have a substrate, this is the bigger substrate, and you would like to deposit let us say the gold you would like to deposit. This is a flat substrate, and the rate of deposition here will be larger than the rate of deposition in this. Okay, so and because of the angle, okay, if you go further and further at this position, this uniformity is better in this case when you do the physical vapor deposition. If this is more closer to that, then the uniformity is not good, but that also depends on the technique. If you are going with the sputtering, in sputtering you won't get anything at this for larger distances, but in case of the physical vapor deposition like e-beam evaporation or thermal deposition, thermal evaporation technique, so you will get a more uniformity at larger distances. Okay. Conformal coverage. In conformal coverage is like how perfectly it is covering this step. Okay, this is the metal that you would have deposited, and this is the SiO2. So how perfectly it is covering this step. Okay, this is the conformal coverage. Okay, this is poor conformal coverage, this is a kind of a good conformal coverage. And now okay, now this is the same thing that is step coverage. Okay, this is if it is perfectly following the step. If you are okay, you have, this is your substrate and there is a step height of this or the substrate, and you are thermally evaporating something material, and you would like to deposit. In that case, what happens is it will go like this, like this, like this. So it won't get deposited over this step on the side of this step. Okay, so this is the case. So when you will get a very poor kind of step coverage, and but you wanted this kind of step coverage, and this kind of step coverage you can get in CVD and atomic layer deposition. In chemical vapor deposition, kind of you can get this, because there are gases, they can go everywhere, they can surround it and can react at everywhere. Okay, but in physically you are taking the material itself to the wafer, so that is the limitation of the physical vapor deposition, and that's why chemical vapor deposition is a bit more better in this case. Okay, so what is CVD? What all sort of things that you require in CVD is like there is a flow of the precursor gas. Okay, and this precursor gaseous environment, and this is a heated substrate. Okay, heated substrate, you can heat the substrate itself, or you can heat the whole chamber. Okay, if you will heat the whole chamber, then there will be deposition on the chamber walls as well, and if you heat the substrate, then there will be a more deposition over the substrate and than the chamber, because the reaction needs to be needs higher temperature that should take place. Okay, so there is over the substrate, this is a susceptor which is of a good quality that can sustain our at higher temperatures. It is kind of quartz or something, so which should not contaminate the chamber itself. So if there are kind of soda lime glasses, there can be sodium or potassium contamination to the wafers. Okay, so which is not desired. Okay, and another thing is at this uh, layer there is a deposition happening, and further we will see there are, okay, what are the things that you need for a CVD. I think there is more slides over that we can check over there as well. Okay, just a minute. Now, so there are heating coils. There is chamber walls to contain the precursor. There are heating coils to provide the energy to the substrate for the reaction to happen, and there is a scepter to hold the substrate, and there is substrate over which you will be depositing your material, and there is a flow of the precursor. There is a continuous flow of this precursor, and that will react with here. And further, there are some sources, there are some bubblers or gaseous sources, and there is the pump that should suck the reacted and non-reacted part of the precursor. Okay. Now, there are for all the system there are some advantages and there are some disadvantages. Okay, so there are more over the advantages of this kind of process, because a very wide range of materials that you can deposit through this. Almost like for every material you can get a precursor. There is one. There are some website like on Sigma also you can check out, on Strem Chemicals also you can check out. There you can find some ALD and CVD precursors over there, and there is a list of precursors with the periodic table. So when you click on the material on the element of the periodic table, then you will get a list of the precursors. Okay, for almost all the elements, all the materials, you will find a precursor. Okay, so gaseous precursor can be highly purified, like gases with 99.999% of purity you can get, and with that you can deposit very good film quality. But on the other hand, if you are just directly buying the silicon dioxide source or metallic source, there is a high chances of impurities in that. Okay, this is a mature technology. Over the years it has matured, and a wide variety of systems came. So repeatability is good. Many people are trying and making more and more kind of good film that we can get out of this system. And deposition is strongly dependent on temperature. Okay, because why uh, temperature plays two roles. One is the diffusion that we will come on, and another is the reaction. The main part is the reaction. Okay, the okay wait the main part is the reaction, that because of at higher temperatures the reaction kinetics gets changed, and that's why. And also good step coverage you can get, because of the everywhere you can find the this gases can go. High deposition rates possible at higher temperatures. Okay, so because if this is reaction rate limited, then you can go you can increase the temperature and you will get a higher rate of the deposition. This does not need high vacuum, and which is the great advantage, because if there are some pumps which are kind of can go up to very less pressure, you can go very high vacuum, and they are very highly expensive as well. So atmospheric CVD you can do, kind of plasma enhanced CVD you can do. They do not require a very high vacuum kind of pump. Okay, so, and on the other hand there are some disadvantages, because high cost, because there are certain things which are very costly in the CVD chamber, which you have precursors. The precursors are really very dangerous. They are explosives. Okay, they are highly pyrophoric, and some kind of gases which are not good for the health of the environment as well. We use them so to for that. and byproducts are dangerous. We need to contain the byproducts, and we need to, after the pump, we should have some kind of scrubber, that scrubber unit that can for the for these kind of gases which are dangerous. They can reduce or oxidize these gases, and with then release to the environment, which are uh, can be done. Okay. And expensive equipment is like sometimes you need to do at the high vacuum, so you should have kind of one two kind of chambers. One is kind of load lock, and another one is a which can run at normal vacuum. Load lock, in the sense, there are two chambers which is separated by a membrane kind of thing, and you load your substrate in the outer uh, part uh, of that chamber. So in that you can the vacuum is not that much high, that can be attained in within minutes, but inside that there is very high vacuum. Okay, so that comes at a price, very high price. Okay, and high running cost, because well, you must have scrubber unit, you must have some precursors, and a lot of things are running during that process. Heater is of high cost, because whatever material you are using inside, that should sustain at the higher temperature. So it is kind of so that's why they are expensive. High temperatures, films are stressed due to the mismatch of the coefficient of thermal expansion, because if you are depositing germanium or gallium arsenide over silicon. Okay, because of the lattice match, when you if you have deposited the silicon over the silicon, the the coefficient, okay, the thermal expansion coefficients are different for both of these, so you will find some films cracky. Okay, that is the thing. And restricted substrates, now in the time of this is a kind of modern world, so you there are more of the things are most of the things are coming with the flexibility. Flexible uh, Flexible watch, flexible sensors, flexible mobiles, okay, foldable kind of things. So you cannot use this kind of technique in for flexible substrates. That's what I want to say. So you cannot do that, and a very few parameters are you can control. So a very few parameters you can control, then you won't have a good control over the system. So that is why only temperature and pressure you can control. With that you can just control the reaction in which regime you are going, that we will see. Okay. Now for CVD, what things you need? First one is the precursor. The precursor is a compound that precipitates in the chemical reaction that produces another compound. Okay, that precursor is it is a um, gaseous precursor. It is a gaseous material, so which flows through the chamber, and after the reaction it converted into solid product, and the byproducts are gases. Okay, and the gases can be taken out through the out of the chamber. Okay, and then substrate over which you would like to deposit. Okay, and that substrate should also withstand till that high temperature, like 1000 or so degrees. Okay, chamber chamber is inert and non-contaminating, like you cannot do these kind of processes in a metallic chamber. So in the metal chamber, what happens is metals can get out, and can some part of the metal can come out, and that can diffuse inside your silicon substrate. The solid solubility of metals is very high in a silicon wafer. So that's the thing. Quartz or steel chambers are usually suffice because they can withstand at higher temperatures. That's why. And susceptor is typically kind of quartz or silicon carbide, so that can withstand with a with at higher temperatures to hold the substrate. Okay, and that should not contaminate the wafer, so otherwise you would not be able to use for the electronic purposes. Okay, heater, that heater can be a heating with the coil heater or IR or RF heater. Okay, most of this is kind of a coil heater over the chamber itself. So you can see. So these are the things that you need for the CVD. And what is the ideal precursor? A good volatile that should react with the at the substrate. Okay, and there should be enough vapors that should be enough vapors in the bubbler, so that can be there. And most of the time what we use is there are some you can say liquid precursor, and some carrier gas is flown through that precursor, and that kind of nitrogen or argon, they will carry the vapors of the precursor to the substrate, and that will react with the substrate. Okay, liquid or gas at room temperature. Okay, it should be liquid or gaseous. If it is gaseous, then we can directly open it without without a kind of carrier gas. Okay, otherwise if it is liquid, then you have to flow bubble nitrogen or argon through that to carry the wafers. Okay, and thermal stability. So if it should be thermally stable, because while transporting it there are some temperature fluctuations, so because of that it should not degrade. Okay, or flow out and decompose cleanly and controllably. So okay, that we will come on like silicon silicon gas that decomposes in silicon 2 and hydrogen. So in that case, that there should be a wide window of the of decomposition. Okay, so that we can have a wide processing window. Okay, and volatile and non-contaminating and stable byproducts. There are, okay, that we will go. So it should be volatile so that it can react at the substrate, and should be readily available, and the main thing is the non-toxic and non-pyrophoric. And almost all the precursors are toxic and pyrophoric. We do not have the precursors which are non-toxic and non-pyrophoric. Okay. So now, what is in CVD mechanism? How does this process works? Okay, what is the mechanism of the CVD? So if you would like to make a CVD chamber, so which things you need to take care, and how you can make the CVD chamber. Okay, so so this is a typical kind of CVD chamber. So that can be a quartz tube itself. So you have kept a wafer in a quartz tube, and from one side of the quartz tube you are flowing a gas. Okay, flowing a gas which is your precursor, that will be continuously flown. Okay, so over the substrate, when there should be a, like, through gas to gas, should be a diffusion of the precursor. Okay, the diffusion of the precursor, of the fresh precursor, from this point to the substrate. Okay, there should be diffusion and adsorption of that precursor at the wafer, and there should be a surface reaction, and then there should be desorption of of the byproducts, and these byproducts should get diffused again towards the flow. Okay, so and then it should be flown out. So this is the main thing that you need to take care, and how you can design, how you can make this diffusion higher, this surface reaction higher, okay, adsorption and desorption. These, how can you control it? You have two parameters, one is pressure, one is temperature. With these parameters you need to play, and you can improve the improve your film quality. Okay, this is the thing. So diffusion to the surface. Okay, uh, how can you get a diffusion to the surface? First, this there is a force flow. At this point there is high pressure of that gas, and at this there is low pressure. Okay, first it will diffuse this gas, because there is a stagnant layer that is there near to the wafer. So that stagnant layer, you or so there that it the fresh precursor should go diffuse from this point to this point. Okay, so that you can control with the pressure of the gas. Okay, higher the pressure, more will be the diffusion of that, and that is the Henry's law. Okay, from higher concentration to the lower concentration it happens. Okay, that is the thing that we will see. So that stagnant layer, this stagnant layer, which is there is no flow of the gases. Okay, here is the laminar flow at this point, but here this is kind of a this boundary layer. Okay, where these gases are stagnant, but there is no flow of very little flow of the gases at this, because of the at this position, at this position there is the flow of molecules is zero, the velocity is zero at these positions. Okay, near to the surface, and because of that there this flow is known a kind of a stagnant layer forms over the substrate, and how which inhibits the flow of fresh precursor from this flow to the substrate. Okay, so first of all, you what you need is this is the reaction chamber, and this from this gas stream to the wafer through this boundary layer, your material should diffuse. Okay, your fresh precursor to diffuse. Okay, and how can you do that we will see. And the boundary layer is created near the substrate where material transport is dominated by diffusion. So how this happens is through the diffusion of the gas through the gas. Okay, this is the thing. So at steady state growth rate, at steady state, and that okay, after this is reacting at the surface, okay, just a minute. This is reacting at the surface, so there are two things happening. One is the diffusion, and another one is the reaction at the substrate. Okay, so these are determining the growth rate of your. So if reaction is good enough, but you are not getting enough precursor to react, then you need more and more precursor. Whatever you have, that is already reacted at this interface. Okay, so what you are limited by is the precursor. How the precursor will come? Through the diffusion. Okay, this is one case. And another case is if you have enough precursor, your diffusion is bit faster, but you do not have the reaction is slow. Okay, so what is limitation is your reaction is not happening that faster, but you have excess precursor at this point. Okay, so that thing is, this is limited by the reaction rate limited, because reaction is not happening that faster. In the previous case, it was the diffusion rate limited, because the precursor was not enough, not sufficient at this position. The concentration of the precursor was not sufficient. Okay, so these two processes, one is the diffusion and reaction is happening at the interface. Okay, so there are these two processes that are depicted by this image. One is the gas flow, gas is over here, and this through the boundary layer this gas is going up to the this substrate interface. Okay, this okay, through this now you can see ng now two things. One is this rate, this thing, the flux of that material, okay, is F1, and reaction for the reaction rate is F2. Okay, so at equilibrium the precursor needs to diffuse across the boundary layer. Okay, this through this boundary layer the flux is F1, we can call it flux. Okay, precursor needs to react at the surface with the flux, so for this flux is F2, so F1 should be equal to F2 for a at the equilibrium. Okay, so if F1 is greater than F2, then there is no need, but at that point F1 should be equal to F2 for at equilibrium. If there is excess precursor, that won't react. If there is reaction rate is faster, that will also not work, but at a certain point these two are equal. Okay, now let us suppose that delta is the thickness of the boundary layer, that is the stagnant layer, and another there is gas flow, so that will come at this position at the substrate. So Cg is the concentration of the gas, okay, in the which is flowing, and C0 is the concentration at the interface. Okay, the flux F1 is given by diffusion coefficient D into Cg minus C0. Okay, and D by and divided by delta. This is the flux. Okay, this is the Henry's constant H, which is equal to D by delta. Okay, this is given by that, and the another flux F2 is given by K into C0, whatever the concentration is available at the interface, into the reaction rate coefficient, that K. Okay, K is the reaction rate constant. Okay, so the growth rate dx by dt is given by Cg by N into 1 over 1 by H plus 1 by K. This is Henry's coefficient. Okay, and this is the reaction rate constant. Okay, this is the growth rate which is given for the CVD. Okay, now we will see different regimes when this is growth rate limited and when this is reaction rate limited. Okay, so okay, before that let's come on the, if your system, you are using a system with multiple gases like selene, oxygen, nitrogen, there are various gases you can use for that. In that we are not dealing with the concentrations, okay, C0, but we are dealing with the partial pressures. Okay, and this partial, we can convert this concentration and partial pressure we can interconvert these things. Okay, the precursors are diluted with the inert gases, and this concentration Cg is equal to Pg by kBt for of each diffusion gas. Pg is different from the P total. Pg is like partial pressure of the gas. Okay, Pg is nothing but the partial pressure of the gas in the gas flow. Okay, in the we can say in the chamber itself. By Dalton's law of the partial pressure, P total is equal to total pressure of the gas that is there is equal to sum of the individual pressures of the gases. Okay, or sum of the partial pressure of all the gases. Cg by C total is equal to Pg by P total, which is equal to Y. That is the, like, from here Cg by C total is equal to Pg by P total, and because kVt is constant from here that you can see, and the growth rate then in that case is given by P total by nkbt into Y. This is kind of formula that you will get from that. Now the main thing that I wanted to tell is, from here this is the formula that you will get. The growth rate is dependent on the partial pressure of the gas, temperature, okay, temperature at which you are doing, the Henry's constant, which is again dependent on the like diffusion. Okay, this H is nothing but dependent on the diffusion that you can see here. H is equal to D by delta. Okay, more is the H, more is the diffusion coefficient. Okay, so diffusion of the gas. Okay, and another thing is that this is the reaction rate constant. More is the K, more is the reaction rate. Okay, so now there comes two different regimes that we will see. So one is if reaction is much faster, and another one is if the diffusion is much faster. Okay, so growth rate, which is given by this formula, P total by nkbt into Y into 1 over 1 by H plus 1 by K. So in this one there are two things, one is H and one is K. Let us suppose at a constant temperature you are doing this thing. Okay, you are not varying the temperature. Okay, so in that case, if H is very greater than K, okay, H is nothing but Henry's constant, and that Henry's constant is giving you the diffusion of the gas through that stagnant layer or the boundary layer. So H is higher, so that means diffusion is much faster than the reaction rate. Okay, so in that case, what this formula will get reduced to P2 in this form. Okay, and this is strongly dependent on the temperature, because the reaction rate, okay, this is because H is very high. So at the interface, what is the limitation? Reaction. Okay, on the growth rate will depend on the reaction only, because the bottleneck is the reaction rate. Okay, now it is dependent on growth rate is dependent on the on this K, reaction rate constant, and that reaction rate coefficient is, or constant is, given by K is equal to K naught e raised to power minus EA by RT. This is kind of Arrhenius kind of plot will be there, and that depends in this thing depends exponentially with the temperature. If you increase the temperature, your reaction rate will be faster. Okay, so in this one, reaction rate limited growth will be and it is very sensitive to temperature, because it is exponentially depending on the temperature. Okay, so this is nothing but just a chemistry that you might have studied in your high school. So that is the thing. And the another regime is the if reaction rate is much faster than that of the of your diffusion coefficient or Henry's constant. So in this case, growth rate is limited by the diffusion, because you do not have enough concentration of your material at the interface, but your reaction rate is much faster. So then growth rate is limited by the diffusion. Okay, this is the diffusion, and diffusion is this is given by H is given by D by delta, and also this D for this diffusion, D is gas in gas. Okay, diffusion of gas in a gaseous material. So in this case, this is very lightly dependent on the temperature. Okay, this does not depend on that much on the temperature, but this depends on the architecture of your how you have placed your samples. Okay, that depends on the flow dynamics of the reactor, or you can increase the pressure, we can say, a bit, so that can increase that thing. Okay, so because this diffusion also this delta depends on the temperature. Delta gets reduced if you have a higher temperature, so and then growth rate will be higher. Okay, so that's the thing. Now here is the now effect of the pressure. Okay, so this is growth rate limited by the reaction because of the H is very high. Okay, and we can say this reaction is very less. So and in another case it is diffusion rate limited. So if for both the cases, PG growth rate depends directly on partial pressure of the gas for both the regimes. But in this case, there is also a boundary layer that also depends on the partial pressure of the gas or the total pressure of the gas. That will also affect that one. And but for almost all the cases, it is a bit you have to increase too much of the partial pressure of the gas or the pressure of the gas to decrease the boundary layer. So it does not depend that much on the pressure. Okay, so higher the partial pressure, growth rate will be higher for all these. Okay, for both of these. Okay, now let's come on the temperature dependence. There are two things that we have two parameters. One is temperature, one is pressure. Okay, so and there are two regimes. One is pressure, we have already seen. The another parameter is temperature. There are two regimes. One is reaction rate limited. Another one is diffusion rate limited. Okay, so in case of diffusion of gas into gas, that does not depend on temperature. Okay, but reaction rate does depend on the temperature. At higher temperatures, this reaction rate gets dominated. Reaction rate is much faster than the diffusion. Okay, so at higher temperatures, this is this is the range of the higher temperature. So reaction rate is much faster, that K is greater than H. So this is limited by the diffusion. Okay, this is mass transfer limited or diffusion rate limited. And at lower temperatures, okay, it is what to say, a kind of reaction rate limited. Okay, this is kind of reaction rate limited because reaction is very slow at low temperatures, but diffusion is still there. Okay, so at in this region H is much greater than K. Reaction rate is very less, so it is limited by the reaction. Okay, in this case. So now so this is the mass transfer limited. So growth controlled by the diffusion to the substrate. Okay, so in this case growth is controlled by diffusion to the substrate. Okay, limiting factor is higher T, and these are the things that you can see. Okay, and another thing is mass transport limited growth. Mass transport limited growth is kind of the diffusion. Okay, if if your material is not getting diffused through this boundary layer, because this boundary layer is also changing with x. Okay, this is the direction. At this delta is more than at this delta. Okay, so so uh, so there at this position you will get a more of the growth than at this position. So there will be a non-uniformity in the growth of the material or the substrate that you do not want. So how can you reduce the non-uniformity of the me- of material growth over the substrate? Okay, this is the growth rate. And how this is given by growth rate is given by Pg by n into d by delta. If this is diffusion limited growth, that is you can say h. Okay, that is h only. Okay, so and d by delta, this depends on the growth rate, depends on the delta. If more is the delta, growth rate will be lesser. So in at this position growth rate will be lesser, at this position growth rate will be higher. Okay, so what you need to see is kind of how can you remove that. What is the click is just if you can put your substrate like this. Okay, if you can put your substrates like this on a wedge. Okay, you make it wedge at the such that your diffusion, this height, this delta is constant throughout. Okay, that is the thing. So in next thing, how so in you can make a wedge kind of susceptor. You can say that susceptor will have substrates over that, and you can have this. And one another thing is here there is some pressure at high pressure, and you are maintaining the pressure kind of thing. Okay, at this is reduced. Okay, this is reduced, that a diameter of that is reduced, and because of that there will be a higher flow of the gas. Okay, faster. So that will this stagnant layer will be lesser in this case. There are several other things as well. No need to go that much in the detail. Okay, and also there are various CVDs. Okay, kind of hot wall, cold wall kind of CVDs. Hot wall in the sense you are heating the whole chamber, and cold wall CVD in the sense you are just heating the substrate. Okay, atmospheric CVD is like you are doing that in the atmospheric pressure. So at that point you have higher pressure, so Henry's diffusion will be higher, so the growth rate will be higher in this case. Low pressure CVD, you have very low pressure, but in that case you will be having more control over that. Good quality of the film you can get, and kind of what to say, the growth rate will be lesser in that case. So in that case that will be diffusion limited or mass okay what was the word is this one, mass transfer limited growth will be there. Okay, mass in this one, mass transfer limited growth will be there. In this case, reaction limited growth will be there. Okay, there are MOCVDs, laser CVDs, plasma enhanced CVD, and atomic layer deposition kind of techniques are also there. So now further we will see the atomic layer deposition as well today. So how it is different from the chemical vapor deposition, and what are the advantages of atomic layer deposition over the chemical vapor deposition. Okay, so now let us see one kind of this hot wall versus cold wall CVD. So in this case let me show you some things. So there is this liquid nitrogen, and just for the hydrogen, and what are they depositing is silicon carbide substrate 3C polycrystalline. Okay, or whatever they are depositing. The thing is, in this one they are just heating this substrate only. not the whole chamber. So here you can just have smaller heaters just to heat the substrate. No need to heat the whole chamber. That will be costly. Okay. And but what is the drawback is, in this case the temperature is not uniform all over the substrate. So if you want a good kind of film, so you need to have or more uniform film, you need to have a uniform temperature, because at lower temperatures reaction will be less, rate will be slower. At higher temperature reaction rate will be higher. A difference in the temperatures will give you the non-uniformity. Okay. And in hot wall chamber, this is the tray, and over that these are the wafers that are there. So there is a gas inlet, and there are some resistance heaters that are completely heating up the chamber. So there is, because of the induction, there will also be heating of the tray or heating of the substrate as well. So whatever gas is going, that there will be a wall deposition as well, and there will be deposition on the substrates as well. Okay. So in this case temperature is kind of uniform, and you will get a uniform growth hole in this one. Okay. So now let's come on the another additive process, which is atomic layer deposition. So give it okay. Now okay. Atomic layer deposition is also called as atomic layer epitaxy. Atomic layer epitaxy, in the sense, there is a that is completely following the whatever the lattice coefficients. Along with the lattice coefficients, it is getting deposited over that substrate. Okay. So this is a layer by layer growth. Okay. In atomic layer deposition, this is a layer by layer growth, in the sense, unlike a chemical vapor deposition. In chemical vapor deposition, both the precursors are coming at the same time, and they are reacting at the heating surface. But in this case, only a single precursor, one by one precursor is coming. Okay, no two simultaneous precursors are there inside the chamber. Otherwise there will be a kind of because of high reactivity of these precursors, they can react in the atmosphere. They are pyrophoric, and as soon as the precursor come in the chamber, both the precursor are there, so they will react, and there will be kind of rain down of the particles or the material or the substrate. Okay, that we will see. And what is the advantage? The advantage is the more conformal, more smoother films are there. Okay. And another thing is low deposition temperatures. At lower temperatures you can deposit zinc oxide, aluminum dioxide, titanium dioxide, and tin oxide kind of precursors. These there are a lot. Okay, this is just I am telling because I know all these I have deposited, so that's why. And also you can deposit some metals as well, some nitrides as well, but for nitrides you need to have a very good precursor of a very good source for the nitrogen. Okay, that can be ammonia, ammonium hydroxide, or kind of precursors can be there. Okay. And let us see. Okay, the another thing is more conformal, as we have seen that it is completely following whatever structure is underneath. Okay, this white layer is zinc oxide, and this is silicon, and this white layer over that, which is a few nanometers, less than 1 nanometer, and it is completely covering the it is following this trench. Okay, whatever step is there, that is it is following. And RMS roughness is less than 1 nanometer, and it is highly conformal and even at the deepest point of the trench. Okay, so this is the thing. So there are certain parameters you need to play with so that you can get a very highly conformal kind of growth in this way. That we will discuss now. Uh, a typical ALD cycle consists of okay, let us see the first what sort of things that you need. Deposition needs two components. One is A and B, and A and B introduced one after other, not together. If you will you will allow them together, then they will react in the air itself and they will deposit. Okay. Reaction between A and B is self-limiting. Self-limiting in the sense that once reacted, A won't react with A and B won't react with B. Okay, A will react with one molecule of B. That is the thing. That is the self-limiting. So we will understand how this is happening. Okay, so initially there is chemi-adsorbed A over the substrate. Okay, chemisorption of a component, and then we will allow the precursor B. This precursor B, A plus B, that there are some molecules of B that this blue will react with red. Okay, only one of the precursor molecule will react with one of the precursor molecule of B. Okay, let me check once. Okay, only one of the precursor molecule is reacting with the precursor molecule of B. Okay, then if we allow some time, so in that all these sites are occupied. All the sites of A are occupied by the precursor B. Okay, these are reacted. Now this B won't react with B. Okay, this B won't react with B, and whatever the precursor is, that will be there, and to remove that precursor we can flow the nitrogen through, and with the nitrogen this can be out. Okay, and then after A plus B we will purge the excess. Okay, we will flow the nitrogen, then this B will be removed, and then again we will give a pulse of A, so that A will react with B. Okay, that A will react, one molecule of A will react with the terminal point of the B. Okay, this will react with B, and each will react. If we allow for some time, the all will react. Okay, then again finally we will get the termination of A. We came at this point. Okay, at this point we came. Okay, so this is the thing. So now so this is the one layer that is grown in these 6 steps. Okay, after this we will after this step we will again purge the system to get the rid of the excess precursor in the chamber, so that if we again pulse the precursor B, it should not react with the excess precursor A that is in the environment. Okay, so this is the thing. So unlike CVD in ALD, we do alternate pulses of these precursors. Okay, in CVD both the precursors come together and they react at the high temperatures. In this case they are reacting at one low temperature, so we cannot allow the two precursors at the same time. Okay, these are highly reactive and pyrophoric, so so care must be taken while dealing with these kind of precursors. Okay. So materials and precursors, let us see. There are certain for vast library of volatile chemicals are there for ALD, and almost as I told you, for CVD there are almost for all the elements there are precursors, ALD precursors. So you can just check with some websites like STREM chemicals. Over that you can find the chemical these precursors. Okay, so the two precursor, one is the precursor which is containing our material that we would like to deposit, um, complex that can be complex of organic material, or organometallic complex that we can say, or that can be some halide like chloride precursor can be there. Okay, like AlCl3, or for another, that is the chloride precursor in trimethyl aluminum is the organometallic complex, organometallic precursor, not the complex, organometallic precursor. This diethyl zinc is also another uh, organometallic precursor, which is for the zinc oxide, and this is for aluminum oxide. This is again for titanium dioxide, titanium isopropoxide, and this is for hafnia oxide, and this is for molybdenum oxide, molybdenum. These kind of precursors are there, and another precursor are the oxides um, to oxidize this material. Okay, there are two precursors. Let us say this is the A, this is B. Okay, so these are the precursor A and B. One is oxidant, one is the precursor that is containing our material that we would like to deposit. Okay, so for nitrides it is ammonia or ammonium, mostly ammonia, because nitrogen you cannot use the nitrogen, because nitrogen has to break the nitrogen it takes a lot of energy. Okay, ammonia can be there, and for sulfide H2S, for phosphides PH3, phosgene gas can be there. Okay, for oxides these are plenty of oxygen containing precursors are there, like H2O, O2, ozone kind of precursors are there. And okay, now let us go some with the how aluminum oxide is deposited using trimethyl aluminum. Okay, so in this case you have a silicon substrate. Okay, if you have a silicon substrate, that definitely will have some OH termination over the substrate, because as you keep it outside outside the environment, there will be some adsorption of the oxygen, and that silicon is converted into SiOH kind of termination. Okay, because there is some native oxide as well as SiO2, and over that this OH termination is there. And when you allow the precursor of this aluminum hydroxide, there will be a Lewis acid base reaction. In this, aluminum has vacant orbitals. Okay, these vacant orbitals, because of these vacant orbitals, it will act as a Lewis acid. Okay, and this oxygen has a lone pair of electrons. Because of that, it will act as Lewis base. So there will be a Lewis acid base reaction, and because of that it will be converted into this form while releasing ammonia, where this methane gas. Okay, this methane is removed, and then it react with water. This as it will react with water, this methane gas again will be released, and you will get this finally this kind of layer over the substrate. This is the one single layer of aluminum oxide, and finally you will get a OH terminated surface, and again you came at this position again. Okay, and this form okay wait this forms a dense and highly conformal Al2O3 coating. Okay, so uh, you can use for some of applications, if where you need to fill the trench, you just need a highly conformal coating over the trench. Okay, so in that case you can use. And this is a layer by layer growth as we have seen. So initially we will give a dose of TMA. That TMA will cover the surface in a self-limiting fashion, and then excess TMA in the chamber will be removed with the help of nitrogen purging, and then we will give a dose of H2O. That H2O will it will react with this TMA over the surface, and it will convert that into Al2O3, and that is the thing, that is the required material, and excess of H2O is again removed with the H2O purge, this with this nitrogen. Okay, material grows layer by layer because of the self-limiting um, this process, because this process is self-limiting. So if you want to fill the trench, you need to give time to go the precursor deep down in the trench, and that will react. So there are two things: there is diffusion through the trench to the trench, and another one is the reaction of and as it is highly reactive species, so the reaction is not a big deal. Reaction happens faster. Okay, within milliseconds this a monolayer of this TMA is covered over the substrate, but you need to have enough of the dose, okay, of TMA, so that we will see what that process. So this is the one step. This is a single cycle of of this ALD cycle. You can say this is the single ALD cycle till this point. Okay, so again we will do this process again and again and again. Layer by layer will growth up to nanometers. In nanometers you can grow. Okay. So, and this is the graph which is shown with the mass gain. This when you do over a crystal monitor, and that crystal monitor you can monitor the mass gain by the crystal monitor. Okay, if you allow the TMA in the chamber, then there is a mass gain on the on the on that your crystal monitor is measured with this one. Okay, so and then this TMA dose, this is the TMA dose, and then because it's gets saturating at this point. Okay, after the saturation you can purge the TMA, so there is no reducing. Okay, if it would have reduced, that means the reaction is reversible, and this reaction TMA with the substrate with the OH termination is kind of non-reversible. It forms a chemical bond. If it would be forming a kind of physical bond, then it would have removed during the TMA pulse. So this step, if it is not decreasing, this mass is not decreasing, that means your TMA is attached with the substrate. Okay, so after that you give a dose of H2O. Okay, and during the H2O dose, so this H2O is reacting with the substrate. Okay, with the, so during that it is also removing the material that we can say methane, and this is the chemisorption, not also again not a physical absorption, but it is forming a chemical bond again, and at that point it is uh, again this is removed, methane is released from that point. Okay, and during that time it is decreasing a bit, and that is the thing. Okay, this is the mass gain in a single step. Okay, in a single cycle this much of mass is gained. This is nanogram per centimeter square that you can see, and this is the mass gain. So this the growth rate, the actual values depends on the growth rate which is there. So depends on the temperature, precursor, etc. But the process is very repeatable. So you can easily control that thing. You can really very easily control. You can make this kind of this in any lab. Okay, you just need two precursor, two bubblers, you just need a chamber, you need MFCs, you need controlling walls, so that those walls can you can control with a some kind of controlling unit, okay, which is you can control through the software the walls. Okay, so you can make these kind of things in any lab, and these are is not that easy, but controlling is a bit difficult, but still manageable. Okay, so ALD growth with the per cycle, as we have seen, there was a gain in mass on the substrate on the crystal monitor, and that this gain in mass, this is for one cycle. Okay, this gain in mass is for one cycle. If we, what if we do the multiple cycles? Okay, this gain in mass, this is constant, this gain in mass, if this is kind of a straight line with the number of cycles, with the time, with the number of cycles also we can say, with the number of cycles, with the time, so this is increasing. Okay, this thickness is increasing with number of cycles. Okay, so that is the thing. And that this is measured as with the growth per cycle. Okay, growth per cycle, how much thickness is increasing with per cycle. Like if you have done 100 cycles, you can measure the thickness with some kind of ellipsometry or AFM or a SAM, these kind of from these techniques you can measure the thickness and then divide by 100, then you will get the growth per cycle. 1.07 angstrom per cycle is they are claiming. So sometimes people get 1.1 angstrom per cycle or 0.11 nanometer per cycle, 0.1112. So that depends on the on your process parameters. Mostly this is you get zero point 0.1, around 0.1 nanometer per second per cycle. Okay, because this is the, that depends on the, sometimes because of stresses or compression or elongation stress, yeah, the bonds may vary. That is a minute can happen. That is the thing. Okay, and a growth rate is linear with the number of steps. Okay, this, that you can see growth rate is linear. That is the beauty of this ALD process. So it doesn't depend on the pressure. Okay, it does not depend on the pressure that much because this is a self-limiting process, and it does not depend, it does depend on the temperature, because that certain window should be there, but during that certain window the growth rate will be constant. It won't depend on the temperature there. Okay, that we will see. Okay, self-limiting nature of the chemisorption. So let us say you have diethyl zinc plus H2O is forming the zinc oxide. So so in this case you have given a dose time. This is the dose time for, this is the dose time, and in this case if you are giving a dose of this is in seconds, let us say this is 1 second. Okay, this dose time is 1 second. That is the kind of a perfect growth. If this is beyond this, if you give dose time 1 second, 1.2 second, 1.5 second, 2 second, whatever is greater than 1 second, that is the, you are wasting your precursor. Okay, that won't absorb over the material, that won't react with the material, that will be there and will get out with the during the per cycle. But if you give a dose time lesser than that, that precursor is insufficient for the, for to cover the whole substrate. Okay, that precursor is insufficient, and for that you need to give a at least that much of the dose time that you this can be done. Okay, that is sufficient for the, to cover the whole surface. Okay, it needs 100% of the coverage. Okay, some time for the 100 that time is in milliseconds only, because the reaction is very fast. Okay, the reaction is too fast, so that can be there. Material does not dissolve much, because as you can see with this thing, so it is decreasing a bit, but that does not decrease that much. So because of the, it is chemically reactive, it is chemically attached with the substrate. So if it would be physically attached, this would have gone out through the through during that pulse cycle. Okay, so and another thing is, if you are giving TMA with this growth rate with vapor pressure, of the dose, this was the dose time and this is the vapor pressure, how much vapor pressure you are keeping it. Okay, whatever vapor pressure you are keeping, 0.1 millitorr or whatever, so that growth rate doesn't matter. Okay, growth rate, if you are increasing the vapor pressure, that growth rate will be same, because of the self limiting. Once a layer is formed, whatever you give, the excess won't affect that much. So if you are giving 0.1 millitorr or you are giving 0.2 millitorr, that doesn't matter. Okay, in this one. Okay, so effect of insufficient dose, that as we have seen, if you are in this regime, what will happen? Okay, if you are in this regime, that suboptimal dose is there, deposition per cycle. So okay, so in suboptimal dose, so this is your inlet, this is your chamber, red thing is your chamber, so you are, this is your inlet and this is your outlet, your towards the pump, and this is near to the dose where sufficient precursor is there. By that time it reaches there, this precursor is not this precursor is not there at all, because it is already reacted at the wafer, and so you need to increase the dose time. So you need to increase the dose time until this you get a uniform deposition. Okay, so so and this is the optimal dose. So optimal dose, so after this point, whatever dose you will give, it will cover the whole wafer. Okay, and growth, the ALD chamber are not designed considering growth dynamics. Okay, growth dynamics is like because this is a self-limiting process. It is not like CVD where you need a kind of wedge for the uniform deposition. Here you will get a uniform deposition up if you are giving a optimal dose. Okay, growth outside ALD window is non-uniform. ALD window is for the temperature as well as for this dose. Okay, if dose is not sufficient, then you won't get a uniform deposition. And another thing is, if your temperature is not sufficient for the reaction, then also you won't get this thing. And another thing is uniformity and conformal coverage. You will get a very highly uniform growth, and conformal coating will be there with a very good aspect ratio. Okay, this the width of this trench is 4 micron and the depth is 114 micron, and still you are getting everywhere, you are getting a very good conformal coating of this thing. Okay, now let's come on the ALD window. What is the ALD window? Atomic layer deposition window. So that for the substrate temperature. Okay, this is the, on x-axis this is the substrate temperature and this is the growth per cycle. So there are 5 regimes. This one, okay, this one uncontrolled growth, because at lower temperatures, what is happening is that the precursor what you have is not volatile kind of, so that will condense over the substrate, and the growth will be more than that the expected. Okay, so because of that there is too much of precursor over that. There is not a monolayer over the substrate, but it is more than one monolayer, and that is why the growth rate will be higher. And at in another case, if if the growth rate, uncontrolled growth, precursor is not reacting at all with that, because at lower temperatures this reaction rate limited. Okay, reaction is not happening at all at the surface. So that is why you won't get a uniform, even not a uniform, you won't get a growth at all. You will get some kind of islands over that substrate, because of the somewhere it is reacted, somewhere it is not reacted because of the less temperature. Okay, and this is the region where you will your this precursor will start reacting at the substrate. And this is the also the temperature for these kind of precursors where there is no condensation is happening at the surface because of the low temperature. Okay, and the another thing is the decomposition of the precursor at very high temperatures. There is a this precursor can decompose, and if it decomposes, it settles down over the substrate and in the solid form, and during the purge cycle it is not getting removed through the nitrogen. Okay, and as soon as the oxidant comes, it reacts and gets settled over that the substrate. Okay, so in that case you will also get the higher growth rate than expected, because of it will happen a CVD like growth. And another one is the desorption of the precursor of after. So so as I told you, that the precursor is reacting with the substrate. Okay, so there was a reaction that is what to say, only forward, no backward reaction is there. Okay, kind of chemisorption was happening, but at the higher temperatures, even that bond can break. Okay, so there certain amount of the precursor that is was chemically attached at the surface can get dissolved during the purge cycle. So, and again you will get some kind of islands or the substrate. There will be no non-uniformity in your on your in your film, and that is why you need to be in this ALD window. So where there is no decomposition, there is no desorption of that precursor, there is no condensation, and there should be some reaction as well. Not some, there should be a proper reaction with the substrate as well of the with the precursor. This is the typical window for diethyl zinc and H2O. Okay, in between what around 120 110 degrees to this is 170 or 180 degrees. Okay, so and this is tantalum oxide with this is the ALD window. At below this temperature it is not reacting, the reaction is not good, and above this temperature it is again desorbing. Okay, and in for tantalum oxide with this precursor, so at lower temperatures the condensation is happening. At higher temperatures this it is a decomposition is happening. Okay, so this is the thing. So after your deposition you can characterize the film with the SEM TEM for morphology, conformality, crystallinity, and roughness, and also you can check the thickness of that. Okay, so there are some these kind of characterizations that you can do for to optimize your system. Okay, to optimize your film. So you can, if you would like to deposit zinc oxide, you need to have diethyl zinc and H2O as a precursor, and because at certain temperature only it reacts. Okay, that temperature window you need to find. Okay, that temperature window will define how you will there will be you will be getting that thing. Okay, and now we are about to close today, so if you have any doubts you can ask me, and that's it for today. uh, Thank you. So if you have any doubts you can ask me. Okay, no doubts.